You met George Nemhauser in 1998, and he gave you some advice about optimization problems. Can you tell that story?
George came and gave a talk, and after that talk, I spoke with him, and I thought, okay, so what do you think are the main challenges for OR right now? And his list was an interesting one because he said, well, we're not really good at providing decision support that is timely. He mentioned multi-objective optimization. So what if I have more than one KPI? And he mentioned decision-making and uncertainty. And that was an interesting one because it's almost 30 years ago now that he came up with that list. And I mean, how much progress have we made on those three fronts?
Hello and welcome to another edition of the Decision Intelligence Lab podcast. Today, our guest is Meinolf Sellmann, a computer scientist, an entrepreneur, and a thought leader whose work sits at the intersection of software development, optimization, machine learning, and intelligent decision systems. He's worked in academia, he's done research, he's been in leadership roles at places like Bell Labs and IBM and General Electric, and he's been an entrepreneur. And currently, he's the founder and CEO of InsideOpt, a startup focused on building solver technologies to solve problems that were out of reach before. And we'll get into some of that on this call. To get us started, I want to hand it over to my co-host, Mike Watson.
All right. Welcome, Meinolf. I want to start with a story you told us. So you met George Nemhauser in 1998, and he gave you some advice about optimization problems. Can you tell that story?
Yes, I can. Thanks for having me, Vijay and Mike. So in 1998, and I think that was the first time I actually met George. It could have been 1999, but if my memory serves me right, it was 1998 where I was there. I was building a MIB solver of all things for Bell Labs under David Gay, who was my advisor there, so co-founder of Ample. Sure, your audience will actually know him.
Yes.
And George came and gave a talk about the use of generalized Gomery cuts in modern MIB solvers. And after that talk, I spoke with him and I thought, okay, so what do you think are the main challenges for OR right now? And his list was an interesting one because he said, well, we're not really good at providing decision support that is timely. So there's often applications where I have like 2 to 5 minutes and I need to make a decision, and we're not very good at making the most of that time. He mentioned multi-objective optimization. So what if I have more than one KPI? And he mentioned decision-making and uncertainty. And that was an interesting one because if you think about it, it's almost 30 years ago now that he came up with that list. And I mean, how much progress have we made on those three fronts, right? Interestingly, there was a workshop, the DECIDE workshop in 2025. I think it was organized by the NSF. At least it's on the NSF web pages. Where they talk about the importance for national security and national competitiveness of providing new forms of decision support. And that list from George is as current as it used to be in 1998.
Have you worked on the multi-objective problem since then? And sort of how are you thinking about it? Is it you like have different weights for the different KPIs? Do you do them in sequence? Like what's your thought on the current state of the art?
Yeah, well, I mean, the traditional is, of course, either aggregate them somehow. So if you do a linear aggregation of multiple KPIs, but that means you're fixing the exchange rate between them, right? So X units of this is favorable to Y units of that.
Right.
And that's not realistic. I mean, if you run a business, you want your KPIs to run between, in the reasonable range. And if you have think of buying a house, right? There's a typical quintessential multi-objective optimization problem. If you're really squeezed in space, but your school district is at 10 stars, and you could go to another one that really makes progress and gives you like 50% more square feet, but the star rating is 1 down.
Yeah.
You're willing to do that trade. If it's the other way around, the school district is in shambles, but you have awesome space, right? You will not do the same trade you would accept the same trade in the opposite direction. Right. So you cannot linearly aggregate objective functions. You can't do it sequential. If you constrain, so if you either make one the primary and everything else is secondary, then it means that you're willing to accept arbitrary losses in the secondary objective function for epsilon improvements on the first one. Not realistic either. Or you could say, well, if you have these kind of, hey, where is the okay range for an objective function? You could say, well, let's constrain one and optimize for the other, right? So those are the three canonical ways of doing it. And that's nonsense, because you don't know what threshold that should be until you actually do the search and you see, well, where can you get the biggest bang for the buck? And that's kind of that's kind of the way how we're going about it. That we're saying, hey, there is a way to get out of the ill-definedness of the problem. It's ill-defined because obviously anything that is Pareto optimal would be a potential solution.
Right.
So you kind of have to get out of there by asking for a little bit more information from the user. The way how we do it is that we just ask them to give us acceptable ranges, or they can be had simply by optimizing for individual objective functions up front and then kind of getting an idea on how well you can get. And then the solver will look for good trade-offs, one against the other.
Okay. Yeah. It seems like a similar approach to your third approach there, where you're looking for, can I give up 1% of cost and I get 20% of something else? And you're like, all right, that sounds kind of reasonable. And you're just putting a little more rigor to that approach.
Well, the problem is that you don't know what 20% is until somebody gave you a range. And that's exactly what we're asking the user to give us. Yes.
Okay, perfect.
Yeah.
Interesting. All right.
Yeah.
So I want to continue down the Nemhauser list, I think. And well, first and foremost, why do we think that there's a renewed focus on decision making after all this noise and all this energy about AI ML for the last couple of decades?
Well, let's maybe start with the latter. Why did machine learning, that's really what it was before all that chat nonsense that's going on right now, why did that hit a nerve? If you ask me, it is because if you run a business, you as the decision maker have to make a lot of those decisions with ambiguous and incomplete information. And it feels like the need that somebody who's asking for decision support feels the most is this question of, could you please just tell me what's going to happen? Can you tell me what the traffic is going to be tomorrow? Can you tell me what the prices are going to be? How much demand can I expect at a certain price? Right? All those things that otherwise become kind of alchemy suddenly seem to have a scientific foundation. And that is why machine learning hit a nerve. And now what people are realizing is that, you can do a lot with data, but you're not going to get perfect forecasts. You still hear some really high ups at very, very large companies asking for perfect forecasts, but it's impossible to get that. The standard example I give for this is, so say you run a supermarket and you have to decide how many sushi dishes you're going to put into the shelf for tomorrow. There is no way for you to know that there are these three young mothers who just had their babies and who got to know each other while they were pregnant and who decided the moment that we can eat this stuff again, we will have the biggest party the world has ever seen. And they just, they walk past your sushi aisle and just pack up everything. There is not enough information in what you can observe to fully forecast what's going to happen tomorrow. Yes. And so the need is still there. It's gotten more precise in terms of what you ought to be looking at. But what people haven't figured out is how to make those decisions given the residual uncertainty that will always be there. And that's kind of our raison d'être, right? This is why we exist at InsideOpt to help do that.
Yeah, I like to think of those problems too. As I ran into that a lot in doing supply chain analytics. It was sort of the premise, like, if we could just forecast demand perfectly, things would be great. I'm like, yeah, of course. And let's build a good supply chain strategy that says you can't forecast perfectly and you never will. What should you do in that case? And it sounds like that's
right.
That's sort of what you're up to, trying to solve those kind of problems.
Yes, it's. There wouldn't even be a bullwhip effect if you knew everything, right? News vendor could pack together and say, like, hey, I know exactly how many newspapers I'm going to sell tomorrow. You don't get that. Right, it's a world that doesn't exist. Thank goodness. If we really knew what would happen tomorrow, that would be very boring. But you have to look at a different place, right? So, and I think that is why there is renewed interest in optimization right now, because machine learning kind of was a letdown.
Well, in a sense that we weren't ever going to get to the level of precision that some people were assuming. But then also, the other thing I would add is that even with near perfect forecasts, we've got a lot of problems with so much combinatorial complexity, right?
Yes.
And and so when you add uncertainty to that, I'd love to get your perspective on kind of the state of the art of solving kind of high combinatorially complex problems in the
Right.
presence of uncertainty.
So when I met George back then in 1998, we had nothing. I mean, there was nothing out there that could address what he was proposing. But then something interesting happened in the late 90s and early 2000s, and that is, of course, the advent of machine learning. So this thought that the machine didn't have to be programmed every last bit, but that it could learn over time how to search these problems better, how to search nonlinear problems, highly combinatorial problems, how to search multi-objective optimization, how to search under uncertainty. That was suddenly on the table, and that kind of became my research agenda. Was to say, can I put statistical inference into optimization? And so we do have a tool for this, but you have to jettison something that the OR community is very much in love with, and that is dual bound. So, kind of an idea of how good am I right now. Plain and simple, because if you have multi-objective optimization, stochastic optimization, or nonlinear optimization, in most cases, those relaxations you're going to get are not going to be very tight. So using them to search is no longer effective. And so what you need to replace it with is a primal tool, right? So don't think about, oh, don't look here, don't look here, don't look here, but replace it with something that says, would you please look here? This looks interesting. Would you please look here? That looks interesting. And that is what machine learning can give you.
So let's dive into a little bit of that. So just to make it a little more general, when you say, what like the current set of optimization tools that you saw like 1998 and going forward were more solving deterministic problems. You'd sort of you define the objective, the decision variables, constraints, and you had solvers like I think you and I overlapped at IBM. So solvers like CPLEX, now Gurobi and FICO that would solve these kind of problems, and they've done lots of interesting things. And what you're suggesting with a primal solver is now you have a tool that considers more nonlinear things directly, considers uncertainty more directly.
Yes.
And what do you mean by primal? So primal is it more just searching and trying to find good solutions within the span of feasible solutions, or what are you trying to do with that? What's your definition of a primal solver?
I mean, a primal solver is essentially a solver that creates either repetitively or initially a solution and then modifies that. Whereas a dual solver kind of thinks about the search space more than the actual solutions, right? So a dual solver will try to eliminate large parts of the search space to not look there. And then, I mean, you kind of force it to dive and make that your priority in a MIP solver, so that at some point you're going to get to the leaf level and will have actually created a solution. But by and large, what the solver does, how it branches, how it partitions the search space and everything, is guided by what can it keep together so that in one piece it can say there is no solution there. And that is not conductive for finding good solutions, plain and simple. I mean, this is why these solvers get complemented internally with heuristics, with primal heuristics, in order to produce solutions that are halfway reasonable in a reasonable amount of time. But those heuristics are not, they're kind of their second thought after the dual solver. And that's why often they are not that effective.
So, one thing that you've mentioned in a previous conversation with me is about the difference between solving a well-shaped technical problem and solving the problem that the business customer actually has. I'm trying to strike the word user from my vocabulary because it casts them as having a mission of using our software and no other. But the business customer has a different problem often than the technical problem we're solving. Um, how do we bridge that gap to create a truly intelligent decision support system?
So models are approximations of the real world. And we make those approximations so that we can handle the computational complexity. That's really the reason why we are abstracting from the real world. And if we limit ourselves to one set of tools, such as mixed integer programming solvers and linear relaxations, then naturally the approximations will always fall in one direction. They will always go towards, well, clip this problem to something that I can solve with a MIP solve. And that is, I mean, we were talking about multi-objective optimization. The things that you do there, I mean, you understand from a business perspective that that is not what is needed, but it's what you can solve, and that's why it gets formulated that way. So I'm frequently dismayed with the fact that OR researchers and also the students that we educate um, kind of think that the advances they should make are on getting the existing benchmarks to solve an iota faster. But that is not the real world, right? The real world, but by the way, this is not limited to OR. This is also true for machine learning. People don't show up with a well-curated Kaggle data set when you're a data scientist. Just, it's not true. I mean, so the kind of the basis you're starting from is off. And so what you need to do if you want to be effective as an OR consultant or as somebody working in a company providing OR expertise is that you need to be able to bridge that gap between the approximation that you can solve with some tool and what the business actually needs. And the art form here is to reformulate the problem in such a way that you're making compromises where it doesn't hurt the decisions.
I was going to ask, sort of the MIP framework, I think, is well known in the space. Like, as you think about what you want to do, like what additional data or variables are you adding that sort of make it more interesting? I have a feeling there's a lot of about uncertainty and sort of distributions of forecast instead of point solutions. But could you expand on that a little bit? Like, what are you adding to the mix there that makes your approach more interesting and more realistic?
Right. So, I mean, the moment that you jettison bounds, suddenly the world becomes very free. I mean, I've lived this MIP world for 2 decades, so I know exactly how you model there. I mean, I wrote 2 MIP solvers in my time. The trade settlement system of the European Central Bank was written with a solution I architected based on MIP. So there's no doubt that you can do a tremendous amount of good with mixed integer programming, but it's just not the is all end all of all optimization. So now if you go and you forget the duals, suddenly you're free. I mean, suddenly you can throw 1,000 cores at a problem, and that works. You just have 1,000 machine learning guided search operators running around and exploring the search space instead of just having 8 that give you a factor of 5, and that's your limit, right? So you suddenly have that liberation. The solver, if you look at the models, doesn't care if something gets nonlinear, if something goes from continuous to integer. It's a lot of the things that you learned are complicating the solution suddenly aren't there anymore. And that's why you can suddenly solve things that are just not doable with a mixed integer programming solver, at least not that I know. We've optimized patient diagnostic path based on false positive and false negatives of tests, priors of what the symptoms suggest, what the person has, etc. In our newsletter, right? So we have this weekly puzzle running. We do things like optimizing the batting orders of a baseball team, which is, I mean, is highly stochastic. The problem that you need to solve there. So you kind of get a lot if you start thinking, okay, look, I have a solution. I'm trying to optimize and improve it. So I mean, now you can formulate more problems, but the real kicker is, of course, that you can also solve them. And the reason why you can solve them is because on the back end there is machine learning going on. And this machine learning is when we started the whole thing in 2006 in earnest, about a decade before it really caught on, the initial idea was what everybody also has, right? So it's like, make optimization faster by providing an oracle. I mean, what's the difference between P and NP? It's the existence of an oracle. So it sounds like, well, to do machine learning in the mix, and suddenly, you're just miraculously going to find great solutions. Turns out machine learning is a bit like counting cards in blackjack. So for those who don't do that, it's like 21, right? So you pull cards and you get 2-3 cards. You can have as many. You can't have more than 21. If you have 21, you win against the bank. And if you go over, then you lose. If you have less than the bank, then that's it. Now, the bank has a prescribed algorithm. So when do they have to pick a new card, and when are they just going to stop and say, well, there we go. You can count cards. So if you knew what cards are still in the deck, you could potentially be in a situation where your odds are better than those of the bank. And those are the times you're going to bet more. So you're going to bet little to learn what the deck looks like. And then the moment that the deck is hot, it's called, you're going to go very hard in. Now, should you bet so the deck is hot. Should you bet all your money on the next game? No. Right? Of course not. Because the thing is still sometimes the bank is still going to win.
Right.
And this is kind of how machine learning goes. It gives you this small edge. It's like, it's a tiny tilt that you get, and you have to let that accumulate over time. It's like in tennis. I think Roger Federer won 80% of his games, but only like 52% of the points or something like this, right? So it's like the individual point you don't want to bet, but for the game, it's a good idea to bet on the guy. And that's what you want. But can you do that in branch and bound when you have very few search decisions to make? It's the early search decisions are very important. You know nothing. So it's very tricky to kind of make machine learning work if you have very few search decisions. Primal solver, looks at 100,000, 1 million solutions over the time that it has to do this. So lots and lots of tiny things that can accumulate in order to make a difference. And that's kind of what allows us to solve these problems and not just formulate.
Yeah, because that's a big breakthrough, right? Everyone's known they've had these problems, but your claim is now we can actually solve them. Yes. Like now I have a method for actually getting an answer. Perfect. Okay. Sorry, Vijay, I interrupted you.
Now, just on that note, how much, Meinolf, do you feel like the advancement has kind of been a consequence of faster computing?
Well, I remember the times in the early 2000s when the Gurobi guys would say, hey, between 1980 and now, we are 1 million times faster, and a factor 1,000 of that goes to hardware, and a factor 1,000 is algorithmic. I haven't made a similar study here for this piece, but what I do know is that even with all the advancements that were made since algorithmically, that as you can find it in the great MIP solvers, on a problem like quadratic assignment, for example, on the Taillard instances, we are over factor 1,000 faster than Gurobi. So if you let Gurobi run for an hour, you're going to get, I don't know, some optimality gap compared to the best known solution. So if you stop Seeker the moment that it's better than what Gurobi finds after an hour, you factor 1,000 faster than the thing. Does that mean that we somehow got a factor 1,000 over Gurobi? No, it just means that the problem wants to be solved with a primal solver, not with a dual solver. Right? So it's very hard to answer that question, Vijay, because it depends a lot on the benchmark that you're after. Then, if you just use the right algorithm in order to solve them, then suddenly you have exorbitant factors. And I wouldn't necessarily say that those are necessarily improvements of the algorithm. It's just that you're starting to use the right tool for a problem.
Yeah, let me take us in a little different direction, but it sounds like you've been working on these problems since 2006, and if you look at your resume, you've been at big research labs, so IBM, GE, and what made you eventually decide to do a startup and sort of create your own solver and go out on your own? Like it seems like a big move. Like what have been the pros and cons of that?
Yes. If I believe that when you do a startup, you have to build up a lot of frustration beforehand.
That's hilarious.
That's a good one.
Well, you have to suffer where you are, otherwise you wouldn't jump. So how do I put this? So in 2016, we had built the first solver for MaxSAT. So this is like the optimization variant of the satisfiability problem that probably everybody knows who's a little bit familiar with NP-hardness, because it was the first problem that was solved, that was proven to be the hardest in all those that you could solve in polynomial time potentially. And we submitted a solver there that was self-learning. So what we did is I programmed that thing, took 2 days, and it would kind of track its progress during the search, but really it knew nothing about MaxSAT other than how to incrementally fast reevaluate a new assignment to the variable. And then I left that thing alone and tuned it for 2 weeks, right? So it's self-tuned. It took the old benchmarks and tried to improve its search. And then we submitted that. We won 4 out of 9 categories against 21 or so other institutions, doctoral students, postdocs, folks who had partly worked on their solvers for 5 to 10 years. And so there is this tremendous opportunity in using machine learning in allowing the machine to learn how to search problems faster. Let's put it that way. So we knew that. I believe. I mean, it was the same year that Alpha Zero, I think, won against the Go guy, and kind of. But we had done it in optimization. I think it was the first time that actually a machine-created heuristic won such a competition. We did that again in 2021 on the AI for TSP competition at IJCAI. So big AI conference, and they had a competition on essentially a prize collection TSP. Now, same story. None of us had ever worked on routing problems before, but we allowed the machine to just go ahead and learn how to solve this problem fast. And so after that, I had enough, because you keep writing these research papers and you see that nobody takes notice. And you go like, well, people could really use this. Maybe we actually need to go and create a product that people can leverage this kind of technology. And that was actually the main reason to say, look, we're just going to jump and create this company now.
Great. You pull some people with you, or is it, did you start it by yourself?
So, my co-founders, if you want to call them that, were the people who were kind of involved in these competitions beforehand. But they're academics. So they had a main job, and they didn't think of, quitting their professorial jobs. And so, in the end, it was just me. But, we are still on good terms, and they still give me, hey, here's a pointer, somebody could use the technology and stuff like that. But
Cool.
the only person who actually said, okay, I'm just going to bet my existence on this was myself. Yeah.
Last question, Meinolf. I mean, you've had a career focused on designing systems to help make better decisions. And how's your own perspective on what constitutes good decision making evolved?
Yeah, that has changed a lot over time. So what I would say is 3 things. Number 1 is only decide what you have to decide. So don't look into the future too much, and kind of halfway commit things that you don't need to lock in right now. As more information comes in over time, you want to adjust your plans. And so it's a good idea to kind of pencil it in, but know that this isn't firm, right? So that would be the first one. The second one is you need to understand which decisions actually lock you in, and which ones are reversible or reversible at a lower cost. This is kind of like when Jeff Bezos talks about it. He talks about one-way and two-way doors. It's very, very important when you do decision making for your life, is to know, well, which decisions are reversibles and which ones are reversible, but only at a very large cost. And then for the latter type of decisions, the biggest thing is to go out of what we normally do, which is like, make it a model and solve the whole thing. The biggest thing that you can do is what you find in every lawyer soap opera on TV. Suddenly somebody has an idea for an action that wasn't on the table these 5 other episodes before, where everybody thought, well, we have to get this witness, right? And that's the biggest thing you can do, is extend your set of actions that you could potentially use in order to get to your result. Don't think within the confines of what you wrote down, what your action set is. Always try to extend that.
Excellent.
Yeah, those are perfect ones. I used to, when I was, when we were doing UpX analytics and there were some problems, that there was this big tendency to try to solve lots of problems all at the same time. And I used to like to think like, all right, let's solve this one, and that other one, it's a real problem, but we'll solve that one when it comes up later. And I think that's what you're kind of suggesting, is like, let's knock off the things that we can knock off now and solve the next problems tomorrow.
Well, and I think it's a really good insight, this idea of what commitments, once we've made them, are super costly and difficult to reverse, which is compared to, let's call it a soft commitment, where the cost of reversing or switching is relatively minor. I feel like very often our problem formulations don't distinguish very well between those things.
Yes, and I mean, if you combine that with the last point that I was making, is you can always think about adding an action that
Right.
makes a solution more reversible, right? So things like, well, I'm gonna lock myself in here, but I'm also gonna hedge. I'm also going to buy some insurance in case that, the world doesn't traverse the way that I want it to be and that I was expecting it to. And consequently, yes, it costs more, right? Insurance is always costly. But at the same time, you don't stand there completely in the rain. Should the world
Yeah.
take a different turn than you wanted it to? Yeah.
I have to say, your
Thanks.
3 decision criteria is, like, so different than what I thought you were gonna say. A guy who develops, like, the ins and outs and the guts of a solver engine, and your, decisions here are, like, things that you could, tell a CEO of a Fortune 500 company, and that CEO would learn a few things. Like, that was kinda fascinating, the two ends. You have quite a range. I'm impressed.
Thank you.
All right.
So, Meinolf, is there where can our listeners find out more about your company, your research?
Yes, I mean, we have a webpage, InsideOpt.com.
Okay.
There is, connect with me on LinkedIn. I always like having more connections there. We have this weekly puzzle. Um, we are launching 2 new products, so lately it hasn't been so weekly, but it's there, and it's. I think even if you look at the archived editions, there, it's quite interesting to see. There's a YouTube channel that we have, and there's even on Spotify some AI crafted, reviews of our users manual and stuff like that. So if you want to start with Seeker, listening to that is kind of an intro. You just get a nicer overview than just leafing through a 50-page user's manual. So yeah, all those resources are there, but the biggest one is probably connect on LinkedIn and follow me there.
Oh, I've got so since you mentioned LinkedIn, I just have to ask it this public. Like, what posts do you write that go viral? Because you write a lot on LinkedIn.
So I
If you
think the
can
biggest
say.
one was a rant on Satya Nadella not understanding what AI is. That was like a three-quarters of a million or something like that.
All right.
Yeah, that was a good one. But the biggest one I was looking in preparation for this call, the biggest one we had on something that's actually related to what we do, um, was um, was a post, actually a very short one, where I voice my surprise that so much in stochastic optimization revolves around expected performance, and there's so very little about risk mitigation. Because really, I mean, the
Mm,
point of optimization is not actually to just get the expected out of the ballpark, but you need to strike a reasonable compromise between expected results and the risks that you're taking on, which kind of ties the whole thing together. I mean, now you see why
Good.
I'm also so obsessed with multi-objective optimization, because there
yeah.
isn't just that one objective, right? So there's this famous gambler's ruin example, where if you take the thing that actually has the biggest return, your chances that you're just going to be bankrupt. But if you take a reasonable mix of things that have lower returns, there's also a puzzle that we had on this one here. And this is what the real world is about. I mean, you're supposed to find a reasonable compromise between different concerns and not knock one out of the park at the cost of everything else.
Well, and in fact, I mean, this does tie kind of much of our conversation together because the decision makers, the business customers, they have to think about the downside, both at the personal level
Yeah.
and at the organizational level. And that lack of trust that they find in solutions that don't consider that is a huge impediment to them
Yes.
moving forward.
But you will find this. I mean, I remember that one of our readers of the newsletter mentioned that I think it was UPS had this problem once, that they needed kind of to determine what fleet of airplanes they were going to purchase or lease, or whatever they were going to do. And they had like 3 different growth scenarios in terms of where they're going to have to ship things, or how much, or something like this. And I think at the time, what the optimization team did was to create an optimal plan for each scenario, and then give them the 3x3 matrix and say, well, this is how this solution would perform under these other two scenarios. The one thing that you wanted to give your stakeholder wasn't there. That fourth row that is a good compromise across all three scenarios doesn't exist if you knock one out of the park and you forget about the other two scenarios. And that's our job, right? This is our job as thinking OR people. What we can also do better than any LLM is to say, look, here's something that properly protects you from the downsides of the world, and doesn't just. I mean, in hindsight, is always going to be suboptimal. But in reality, it is with the state of knowledge that you have now, it's the best solution that you can provide.
All right, this segment's a little bit unique. So Meinolf, I'm going to turn it over to you. And can you tell us this complicated scheduling story where your solver and your approach really kind of came in and won the day?
Right. So this is a real story. A company that roasts coffee. And they have a number of roasters, and they have a limited amount of silos where the roasted beans cool off before they can be weighed and packaged. And they wanted to get the utilization of their roasters up because they were standing still a significant amount of time. So they solved the whole problem with mixed integer programming. And mixed integer programming, the solutions looked very good, but what the company actually found is that in practice, they weren't. And then when they looked into it, they saw that the operators was deviating from the plan significantly. So they were asking why that was, and the reason was that the operators just weren't able to follow the plan. Particularly, what was the reason? When you have freshly ground coffee and roasted coffee and throw it on top of other coffee that was maybe already cool, then you're reheating that. And that meant that the coffee that they could extract from a silo would be warmer than they wanted it to be, and they couldn't package it at that time. That meant that the silo wasn't empty and they couldn't throw other beans in there. Now, with a mixed integer programming solver, that's very hard to model, right? If you think about it, it's like, you throw coffee on top of other coffee, and now a certain part reheats and others do not. With a primal solver, you really don't have that issue at all. Because what you do is in our software, you would just add a user-defined function. So in a vector, out a vector. So what that function would take is something like, well, what were the layers in the silo before? What was added? What was taken out? And what are the new layers and comes out? Right? That would kind of be the way how it is. And you see how close to reality to the actual system you are. And that is what gives you the speed with modeling. And
I would imagine that constraint is a very hard one to model in MIP. It's probably very nonlinear. It's a lot of physics. The physics of cooling has to be involved in that function.
Yes, but even if you did it simple and you just say, hey, whenever you add coffee on top of other coffee, I don't know, the top two tons or so get reheated and need to reset. It's not easy to actually do that unless you time bound thing.
What's then interesting about the primal, if what I understand, your primal solver, is that in a situation like that, what you're looking for is you're trying to search the space of feasible solutions. You're looking at millions and millions of feasible solutions. You have intelligent ways to find good ones or bad ones, and that gets a plan to the coffee roaster that they can actually implement.
Yes. So, I mean, what you would do in this case, and that's really important, also ties into some of the other things that we've been discussing. If you said, okay, we're going to break down the whole production schedule into sub-jobs where we just say we need to roast X tons of this and then X tons of that and just prioritize it. Now you can execute this kind of plan without going overly minutely into every detail. And what really happens is that the solver would pick such a sequence and a design of the jobs and simulate what would happen in the factory. Just as you simulate what will actually happen, with your design, or what will happen with the train yard, if you set certain start times or end times, and kind of do certain snippets and something like that. You simply simulate out what happens in your actual system. It makes it insanely fast. I think this is particularly important to everybody on the who's listening to this, who's creating optimization models for a living, because that kind of speed is what wins trust. right? The higher the urgency of the people who come to you to ask for help, the shorter and narrower the window is within which you have to deliver. Because if the urgency is high, these people will find a workaround to solve the thing. So if you're working 2 months on a beautiful Benders decomposition for your problem, the problem has evaporated by the time that you're ready with your solution. And we have a not small amount of clients who are actually using Seeker almost primarily for the reason to win that initial phase where you have to react quickly and show the client very quickly that you're listening to them, and that you can, in very short amount of time, get close to something that they could actually execute.
Perfect. All right. That was great. I wanted to get that story out there. So I appreciate you hopping on and doing that story.
Pleasure, Meinolf. Great to have you.